Welcome, dear learners, to this first video of elementary quantum mechanics. In this video, we will discuss two important phenomena, that is black body radiations and photoelectric effects. So before that, we will quickly discuss about some introductory part of this quantum mechanics. In the late 17th century, Isaac Newton discovered classical mechanics, that is the science of motions of macroscopic object, or it is also called as large object. This classical mechanics successfully explain the motions of object from planets to our everyday objects such as moving car, cycle, cricket ball or football, etc. However, towards the end of 19th century, classical mechanics was unable to correctly describe the behavior of microscopic particles such as electrons and nuclei of atoms and molecules, that is subatomic particles such as protons, etc. So there is efforts in the direction to study the motions of microscopic objects which give rise to the birth of new branch that is called as quantum mechanics. It is also called as modern physics. So quantum mechanics come out as a great discovery of 20th century. The term quantum mechanics is made up of two terms, that is quantum and mechanics. We know that mechanics is referred as the science of motion of an object, while quantum is a Latin word which is means by an amount. And in modern convention, it is used to represent smallest possible discrete unit of an physical property. So quantum mechanics replace classical mechanics at the atomic or subatomic level. It gives the law of motion of microscopic object, similar to the laws given by the classical mechanics. So quantum mechanics is therefore the theoretical science of microscopic matter. Now we discuss the differences between classical mechanics and quantum mechanics. So it will make easy uh, to understand these two branches. Classical mechanics deals with the motion of macroscopic particle, that is called as big particle, large particle. While quantum mechanics deals with the study of motions of microscopic particle, or we call it as a minute or small particle. Classical mechanics is based on Newton's law of motion, while quantum mechanics is based on Heisenberg uncertainty principle, de Broglie's concept of dual nature of matter. Classical mechanics is based on Maxwell's electromagnetic wave theory, according to which any amount of energy may be emitted or absorbed continuously. While quantum mechanics is based on Planck's quantum theory, and according to which only a discrete, that is discontinuous value of energy are emitted or absorbed. In classical mechanics, the state of the system is defined by specifying all the forces acting on the particle as well as their position and velocities. While in case of quantum mechanics, it gives probability of finding particle at various locations in a sphere. Now, what about this Maxwell's electromagnetic theory? We quickly discuss some postulates of this theory. According to Maxwell electromagnetic theory, electromagnetic radiation propagate in the form of waves only. It consists of electric and magnetic field perpendicular to each other. These radiations travels through empty space. Waves other than electromagnetic waves have to travel through some substance. For example, Sound wave will need either a liquid, solid, or gas as a medium to pass through it. The speed of light, which is 3 into 10 raised to 8 meter per second and is always constant. Wavelength is commonly characterized by the symbol lambda. It is measured between the distance of either crystal or trough. Next is Planck's quantum theory, on which the quantum mechanics is based. According to the Planck's quantum theory, different atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiation is called as quanta. The energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiations. Either energy get absorbed or emitted, and it is directly proportional to the value that is called as frequency. Meanwhile, the energy of the radiation is expressed in terms of frequency as E is equal to h mu, that is called as Planck's equation, where E is the energy of the radiation, h is Planck's constant, whose value is 6.626 into 10 raised to minus 34 joule second, and mu is the frequency of radiation. So with the help of this, we can calculate the energy of electromagnetic radiations. Now, black body radiations. This is one of the important experiment. The object which absorb and emit the radiation of energy completely is called as black body. Particularly, it is not possible to construct a perfect black body, but a hollow metallic sphere coated inside with a platinum black with a small aperture in it can act as a nearly black body. So when the black body is heated at high temperature, it emit radiations of different wavelength. See here, it consists of a sphere having a small aperture through which radiations can enter inside this black body, and inside it is coated with a platinum black, carbon black, which absorb maximum radiations and emit zero radiation. That is not perfectly black body, but it is close to ideal black body. When this black body is heated, it start emitting radiations. So following curves are often when the intensity of radiations are plotted against the wavelength at a different temperature. So when black body is heated at very high temperature, it start emitting radiations of different wavelength. Initially, it start emitting red radiation, then yellow, and afterwards it become blue, and at the end it become white. So it start emitting radiations of different color at different temperatures. See here, in this way we observe different rays, different color radiations emitted from that body. Following are the conclusion that can be drawn from the graphs. At a given temperature, the intensity of the radiation increases with wavelength and reaches a maximum value and then start decreasing. With increase in temperature, the wavelength of maximum intensity, that is lambda max, shifts towards lower wavelength. According to the classical physics, energy should be emitted continuously and the intensity should increases with increase in temperature. The curve should be as shown by dotted line. In order to explain the experimental observation, Max Planck proposed the following theory, that is quantum theory. Energy is emitted due to the vibration of charged particle in the body. The radiation of energy is emitted or absorbed discontinuously in the form of small discrete energy packets, that is called as quanta. Each quantum is associated with definite amount of energy, which is given by the equation E is equal to h mu, where h is Planck's constant, mu is frequency of radiations. The total energy of the radiation is quantized. That is, the total energy is an integral multiple of h mu. It can only have the value of 1 h mu, 2 h mu, or 3 h mu, where n is 1, 2, 3, 4 even integer, and it cannot be a fractional multiple of h mu. Energy is emitted and absorbed in the form of quanta, but propagated in the form of waves. Now, Stephen's Boltzmann law gives a relation about the energy emitted from heated black body and temperature. So it clearly gives a relation between the energy emitted with respect to temperature. So on the basis of experimental studies, scientist Stephens in 1879 shows that the total amount of energy E radiated by a perfectly black body per unit area per unit time is directly proportional to the fourth power of its absolute temperature T. That is, E is directly proportional to T raised to 4, or E is equal to rho T raised to 4, where rho is universal constant that is called as Stephen's constants. And its value is 5.6697 into 10 raised to minus 5. If energy is expressed in Earths, time is in second, and area is in square centimeter, the above statement is called Stephen's fourth power law or Stephen's Boltzmann fourth power law. The theoretical proof of this law was given by Boltzmann using the law of thermodynamics. Another law that is called as Wein's law gives us information about the wavelength and temperature. The wavelength lambda m for which the emittance of a black body is maximum is universally proportional to its absolute temperature. This is called Wein's displacement law. Mathematically, the law may be represented as lambda m is directly proportional to 1 upon T, where lambda m is equal to wavelength corresponding to maximum radiations of energy and T is equal to temperature on Kelvin scale. This is observations of black body radiations. Another phenomenon that is called as photoelectric effect. Before discussing this photoelectric effect, we should know some basic information about photons. So according to the quantum theory, light is not continuous, but it is discrete and consists of small bundle or packets of energy that is called as photons. What are the properties of photons? A photon always travel with the velocity that is equal to the velocity of light. Photons are electrically neutral. They cannot be deflected by electric or magnetic field, and they do not ionize. Rest mass of a photon is zero. Energy of photon is calculated by the value by the equation E is equal to h mu, or E is equal to hc upon lambda. So lambda is remaining there. Mass E is equal to mc square, that is also used to calculate the energy. We can modify the equation for mass. Mass E is equal to E upon c square, or by putting the value of hc upon lambda, we can write mass equal to h upon c into lambda. And in terms of momentum, P is equal to m into c, and that is equal to by putting this value, we can modify it for momentum also. Now, what is photoelectric effect? The emission of electron by metal surface when exposed to light or any other radiations of suitable wavelength or frequency is called as photoelectric effect. What is Einstein photoelectric equations? According to Einstein's equation in photoelectric effect, one photon is completely absorbed by one electron, which thereby gains the quantum of energy and may be emitted from metal. The energy of photon is used in two parts. Parts of its energy is used to free the electron from the atom and away from the metal surface. This energy is known as photoelectric work function. Other part of energy is used to gain the kinetic energy to the electron. Therefore, H mu, that is the energy supplied by the radiation, is used to perform work for ejaculation of electron from metal surface, and the rest of the energy is used to give the kinetic energy to that particular electron. So in this equation, W is the energy required to overcome the attractions, and kinetic energy is the kinetic energy of the electrons. This equation is known as Einstein's photoelectric equation. When the photon's energy is of such a value that it can only liberate the electron from metal, then the kinetic energy of the electron is zero. Here is called as threshold frequency. So threshold frequency is defined as the minimum frequency which can be used to cause or to produce photoelectric effect. Since the frequency corresponding to the minimum energy required to overcome the attraction is called as threshold frequency, it is denoted by mu zero. The above equation can be written as h mu equal to h mu zero plus kinetic energy. So we can modify it, and after modification, instead of kinetic, for kinetic energy, equation become h mu minus h mu zero. Therefore, h is equal to mu zero minus mu. Okay, so in this way, uh, the equation is modified, that is called as Einstein photoelectric equation. So Einstein gave the explanation for the photoelectric effect by considering the uh, particle nature of that wave. So this is all about these two important experiments in quantum mechanics, that is black body radiations and photoelectric effect. Thank you.